Hello and welcome to the Grade NAT44 demo for BNG subscribers on ASR9000 system. In this demo, I'll show you PPPoE subscriber traffic passing through the Integrated Service Module, in short ISM, which is a service delivery platform to host services like carrier-grade NAT. We will also look at two use cases. Use case 1, BNG subscribers terminating on a VRF. Use case 2, BNG subscribers terminating on a default VRF. I'll also show you accounting and logging of translation information. We'll also look at high availability aspects of this feature. Let's look at use case 1. The network for the demo comprises of a PPPoE simulator, which is connected to a switch through a single link. The switch also has a bundle Ethernet termination on ASR9000 BNG. The ASR9000 system also has a ISM module which is hosting NAT44 service. In this use case, the subscriber traffic arrives on a VRF which is also mapped to the NAT44 instance. The PPPoE subscribers are assigned private addresses from the range 10.1.0.0/16, and the source address pool used for translation is 100.1.2.0/25. So we have around 128 public addresses for translation. We also have a radius server for authenticating the PPPoE subscribers. There is a default route to push the subscriber traffic into the ISM module for NAT function. The next stop is the service app interface, which is a service virtual interface on ISM module. And for the traffic coming from the internet, there is a static route with next hop pointing towards another service app interface for reverse NATing. Let's take a look at a demo. In this use case, the subscriber traffic enters the ASR9000 BNG on a bundle Ethernet interface, which is on a VRF iVRF. You can see that the same VRF has been mapped to the NAT44 instance on the ISM module. In the traffic generator, I have simulated 64,000 PPPoE subscribers. I have enabled the simulation on traffic generator. Let's wait for the sessions to start getting established. We can see that the PPPoE subscriber session establishment has started. Let's go to the router to check the same. We can see that the PPPoE subscriber sessions are getting activated. Let's wait for the 64,000 subscriber sessions to get activated. Let's check the subscriber sessions. We can see that 64,000 PPPoE subscriber sessions have been activated. Let's check the subscriber routes in VRF table. We can see that 64,000 subscriber routes are present in VRF table. Let's check the traffic generator. We can see that there were 64,000 sessions attempted and the same have been established. I have created a traffic mesh for 64,000 PPPoE subscribers, each having a single UDP flow. Now let's start the traffic generation. As you can see here, when the subscriber traffic passes through the ISM module, the NAT44 translation entries are created. You can see that here there are 64,000 active translations for 64,000 PPPoE subscribers. We can also see here that 128 public addresses are used for the translation. So the 64,000 PPPoE subscriber IP addresses are compressed to 128 public IP addresses. Let's look at NetFlow logging. We have configured 10.64.81.232 as our NetFlow collector, which is listening on port 10,000. Let's go to the NetFlow collector. This window is log session for NetFlow collector, which is listening on port 10,000. Let's go to the traffic generator to start the subscriber traffic. We can see that as soon as the translation entries are created in ISM module, the create data is logged to the NetFlow collector. The create data consists of private IPv4 source address, translated IPv4 source address, the inside port, the translated outside port, and the protocol type 17, which is UDP in this use case. Now let's look at logging of delete records. We need to stop the traffic and wait for the sessions to time out. As soon as the sessions get timed out, the delete records are sent to the NetFlow collector. The delete record consists of IPv4 source address and the source port and the protocol type of the translation entry which is deleted. Let's take a look at use case 2. In this use case, the BNG subscriber traffic arrives on a default VRF. The NAT44 implementation on ISM module expects the traffic to be on a WRF. To meet this requirement, we make use of a feature called ACL-based forwarding, wherein a match is done for the source address of subscribers and the traffic is pushed to the next stop, which is in the WRF. Let's take a look at the demo. In this use case, the subscriber interfaces are created in a default WRF. Let's also check the subscriber routes. We can see that there are 64,000 subscriber routes in a default WRF. Let's check the translations. We see that currently there are no translations. Let's start the traffic. We see that as soon as the traffic passes through the ISM module, the NAT translations are created. Let's look at the high availability aspects of this feature. We will bring down the active route processor so that the standby route process takes over and there is no impact on the data plane and the sessions. This particular command will force the switchover from active RSP to the standby RSP. You can see that the standby RSP is taking over. Let's keep a watch on the traffic generator as well. We can see that there are no traffic drops reported in the traffic generator when the failover was triggered. We can see that there are 64,000 active translation entries for PPPoE subscribers remain intact. We can also see that the standby RSP has taken over as active. Thanks for watching this demo.